Hi everyone. The next thing we want to work on is getting just a little bit of familiarity with the number e. This is a number that has some really beautiful properties and it's incredibly interesting in calculus. But for now, we're going to work our way up to it through an application. One of the really nice applications of this number, and it's definitely not the only one, but it's compound interest. So we're going to play around a little bit with compound interest and get a compound interest formula and use that to build up to this idea of this number e that is similar to the number pi in that it's a very useful number, but it's a non-repeating, non-terminating decimal. So we can't write it out longhand, so we give it a symbol. So pi is roughly 3.14. I'm guessing we're all pretty comfortable with that at this point. We want the same relationship with the number e. Okay, so compound interest. Let's start with something fairly simple. We have $1,000 and we're getting 6% annual interest. And the first question is, how much money do we have after 1 year? So we want to think about this in the exponential way. If you start with $1,000 and you increase that by 6%, that's the same as multiplying by 1.06. So we're going to end up with 1,060. So we get $60 in interest. We end up with 1,060. The next question is, what happens if you get this 6% annual interest every year for 3 years? And this is where we start to see compounding. So to get our balance after 2 years, we could take that 1,060 and multiply it by 1.06. And then we would multiply that answer by 1.06. But if we want to summarize that and start to try and build our exponential function, at the end of 3 years, you should have increased by 6% 3 times. So we get this 1,000 times 1.06 cubed, and I get from that approximately $1,191.02, 0.016, so rounds up to 2 cents. Okay, so that's interesting, and what we see is that we don't just get the $60 3 times. There is a situation where you would get that. For simple interest, you just get the 6% on the original amount paid to you over and over and over again. So you'd get $60 at the end of 1 year, and then another 60 and another 60. But compound interest builds on itself, and this is generally what we really have going on. So where we can start to get into even more interesting questions is that often banks don't just calculate the interest once a year, they might calculate it more often. So we could ask the question, what if we go back to that $1,000 invested at 6% for 1 year, but now we compound our interest twice during the year? Do we still get the $60 in interest? So we're saying that instead of getting 6% at the end of the year, we get 3% in the middle of the year and then another 3% at the end of the year. So we take our interest, and since we're doing it twice, we cut it in half, so now it's a 1.03, 3% interest, but we do it twice during the year, once at the 6-month mark and once at the 12-month mark. And what happens here is you get just slightly more money. So I got the $1,060, and then I got an additional 90 cents because I earned interest on that 3% interest that I got. So I got $30 in the middle of the year in interest. And then at the end of the year, I wasn't just earning interest on the $1,000, but instead on the $1,030. So it's not a ton. It's just 90 cents more, but it's a little bit better. So then the question becomes, how far can we take this? What if we compound monthly or weekly or daily? So this starts to build up the way we calculate compound interest. So if we want to compound monthly, that's 12 times during the year. So we want 1 plus whatever the rate is that we're going to get every month. And to find the rate, we'll take our 6% that we were starting with for the whole year, and we'll divide it up over the 12 compoundings that we're going to get. And then since we're only doing this for 1 year, it will happen 12 times. So that's going to give us our calculation for monthly. For weekly, there's 52 weeks in a year. So we would do it 52 times. So we'd have to now divide the 6% over 52 weeks and then apply it 52 times. And if we wanted to go down to daily, we'll just do 365 days. That should give us the idea. So divide your 6% interest over 365 days and then apply it 365 times. And from these calculations, I get 1,061 and 68 cents. I get 1,061 and it rounds up to 80 cents. And then I get 1,061 and 83 cents. And you can see that it does keep climbing, but I'm increasing the number of compoundings a lot, and I'm getting smaller and smaller increases in the amount of money that I actually get. So what we want to do is take this all the way to its extreme. So first thing, let me give you the compound interest formula. The amount that you're going to have after t years is your principal, whatever you started with, or here, let's do it more Math 141 and less businessy. Initial amount, that subscript 0, that's really popular in science. That's for initial amount. So initial value, just like usual with our exponential functions. And then we have 1 plus our interest rate, and that has to be written as a decimal, divided by the number of compoundings per year. And then you raise that. Basically, you're trying to raise it to the total number of compoundings that have happened. So in all of the examples I wrote down, I was doing 1 year. If you want to do more than 1 year, you're just going to multiply the number of years by the number of compoundings per year to get the total number of compoundings. So this is years. Okay, so that's the compound interest formula. And the part that really matters in here is what happens to the 1 plus r over n to the nt as n gets really, really big, infinitely large. So if we do more and more and more compoundings, not 52, not 365, we start looking at 1,000,000 and 1,000,000,000 and 1,000,000,000,000 and so on. What happens to this thing? And the answer is that this is when the number e pops out. This approaches e to the rt. So we can have what we call continuously compounded interest. Okay, I'm running out of room, but continuously compounded interest. That formula is initial amount times e to the rt. And what we find is that that number e that we get that makes this work out is roughly 2.7. To give you a little bit more, it's 2.7182818, blah, blah, blah. It looks like it's going to make a pattern, but it doesn't. This is called Euler's number. It's got a funny spelling. It looks like Euler. And it is a really, really important one. You'll see it used for population growth and all sorts of things. I want you to know that it's roughly 2.7. I want you to know that it's not a variable. And I want you to be able to use it in these formulas. The only other thing I want you to be able to do for the purposes of what we were just working on is to be able to look at y equals e to the x as a parent function. Since e is bigger than 1, this will be an exponential growth function, and it will go through 0, 1 like the rest of them. It will have a horizontal asymptote at y equals 0, and then your other points are going to be a little bit funny. It will go through 1e, which is really close to 1,3. It's just a little below that, right? E is about 2.7, so that's roughly 1, 2.7. You should label it exactly with the e, but you should know in your head that it's about 2.7. So you're placing that point approximately, but you're labeling it exactly. Okay, so keep these two formulas jotted down somewhere. We'll play around with them a little, not a ton, but a little, because it is a really nice exponential application. And then we'll go ahead and do another example to work through a transformation.